All right, let's get right into it. We're going to talk about one of the most fundamental ideas in all of artificial intelligence, search algorithms. Now, I know it sounds a little dry, but trust me, this is the absolute core of how an AI thinks, how it plans, and how it solves pretty much any problem you throw at it.
So really, how does an AI solve a problem? When a GPS finds you the fastest route or a computer beats a grandmaster at chess, what is actually happening under the hood? Well, it turns out the whole process is way more relatable than you might think.
I want you to imagine you're at the entrance to a gigantic, sprawling maze. And somewhere deep inside, there's a treasure chest. That treasure, that's the solution. For an AI, almost every single problem looks just like this maze. The starting point is the problem, the treasure is the answer, and all those winding paths and dead ends are the countless choices it has to make to get there.
So here's our plan for navigating this idea. First, we'll look at the core challenge. Then, we'll see what happens when the AI is basically searching in the dark. After that, we'll give it a compass, tackle some tricky games and puzzles, and finally, bring it all back to see how this stuff shows up in our world every single day.
Okay, so the main goal here is really simple on the surface. Find a workable path through this maze of possibilities, from the beginning to the end, from the start state to the goal state. And in the AI world, we just call this whole process search. And look, AI search isn't just taking random guesses and hoping for the best. It's a systematic, logical way of exploring what we call the problem space, which is really just a fancy way of saying the entire map of the maze. Without these structured search methods, an AI would just be lost, wandering forever. This is literally the foundation of how AI solves problems.
Let's start with the absolute hardest version of this challenge. Imagine our little maze runner has no map, no compass, not a single clue about where the treasure is. They're completely in the dark. All they can do is follow one simple rule over and over. This is what's called uninformed search, or, my favorite, blind search.
Okay, so our first blind strategy is super cautious. It's called breadth first search, or BFS. Here, our maze runner checks out every path that's one step away from the start. Then, once that's done, they check every path that's 2 steps away, and then 3, and so on. It spreads out like ripples in a pond. The great thing about this? It guarantees you'll find the shortest path to the treasure. The downside? It can use a ton of memory, keeping track of all those different paths at once.
Now let's meet the total opposite, the risk taker. This is depth first search, or DFS. Instead of carefully checking every option, our maze runner picks one single path and just guns it, going as deep as possible until they hit a dead end. Only then do they backtrack and try another path. This is way easier on memory. But there's a big risk. It might dive down an incredibly long, pointless path and get stuck wandering for a very long time.
So here's the head-to-head comparison, and it really lays out the trade-offs. BFS is your cautious explorer, going level by level, which is perfect for finding the shortest route, but is a total memory hog. DFS is your speedy diver, plunging down one branch at a time. It's light on memory, but might get completely lost. See, there's no single best way to search when you're blind. It all depends on the shape of the maze you're in.
All right, searching in the dark is tough. But what if we could give our maze runner a little bit of help? A hint? A nudge in the right direction? What if we gave them a kind of magic compass that always pointed roughly towards the treasure? Well, that's where informed search changes the game.
That magic compass has a technical name, a heuristic. A heuristic isn't a perfect map. It's more like an educated guess, a rule of thumb. It gives the AI a general idea of which direction looks the most promising. This is the secret sauce that makes informed search so much smarter and faster than just fumbling around in the dark. Seriously, just think of it like that magic compass. If you're in the maze and the compass says the treasure is generally that way, you're naturally going to try paths that head in that direction first. A heuristic gives an AI that exact same kind of intuition, letting it make intelligent choices instead of wasting time on paths that are obviously wrong. And all of this leads to the undisputed champion of informed search algorithms, A-star. A-star is so clever because it combines the best of both worlds. It looks at the actual cost of the path you've already walked. Then it adds that to the estimated cost to get to the treasure. That's our heuristic. You add them together and you get a score. The AI just follows the path with the lowest score. It's this beautiful balance of what you know for sure and your best educated guess. So why should you care about A-star? Because you use it pretty much every single day. Every time your phone's GPS calculates the best route to work, avoiding traffic, it's running a version of A-star search. It's weighing the miles you've already driven against the estimated time left on different routes. It is the absolute gold standard for a reason.
Okay, So finding the best path is one thing, but what if the maze itself gets more complicated? What if there's someone else in the maze actively trying to block you? Or what if some paths are locked and you need to find the right keys first? Well, this takes us to a whole new level of search.
This is the world of adversarial search. We see it all the time in two-player games like tic-tac-toe or chess. The AI isn't just trying to find its own path to winning anymore. Now it has to think ahead and predict the moves of a smart opponent who's trying to do the exact same thing to them.
The classic way AI handles this is with an algorithm called Minimax. It's kind of wonderfully paranoid. The AI, the max player, looks a few moves ahead. For every move it could make, it assumes the opponent, the mind player, is a genius who will make the absolute best move to shut them down. So the AI picks the move that gives it the best possible result in that worst-case scenario. It's basically planning for the worst and hoping for the best.
But hey, the challenge doesn't have to be a person. Sometimes the maze itself just has a bunch of tricky rules. This is what we call a constraint satisfaction problem. Think about Sudoku or trying to create a class schedule for a whole school. The goal isn't just to find any path, but to find a path that obeys all the rules, like no two classes in the same room at the same time.
So, as you can probably tell by now, this whole maze analogy is incredibly powerful. And the really cool thing is, once you start to recognize it, you see these search problems and their AI solutions absolutely everywhere. I mean, the applications are just all over the place. GPS navigation is A*, the AI in video games is using Minimax to challenge you. The internet itself uses algorithms like breadth-first search to route information around the globe. And huge logistical puzzles, like figuring out flight schedules for an airline, are massive constraint satisfaction problems. These algorithms are the quiet, invisible engines running so much of our modern lives.
So after all this, what's the big takeaway? It's that there is no single best search algorithm. It's always a trade-off. You have to ask, do I need the absolute 100% perfect solution no matter how long it takes? That's optimality. Or do I just need a pretty good solution like right now? That's speed. And how much computer horsepower can I afford to use? That's memory. Choosing the right algorithm is all about understanding the maze you're trying to solve.
And this quote really just nails it. At the end of the day, search isn't just about a computer crunching numbers. It is the fundamental process that lets an AI act intelligently, to look at a complex situation, to weigh its options, and to choose a path forward. In a very real way, it's the bedrock of machine reasoning. And that kind of leaves us with a huge, fascinating question. All of these incredible algorithms are designed to find the best path in a maze that has clear rules and a defined treasure. But what happens when you have problems with no single right answer? Problems of creativity or morality or complex human emotions? What does an AI do when there is no best path? Well, that's the next great challenge, isn't it?